Here is today's problem. We must find the value of x in this exponential equation. We have 4 to the x times 16 to the x equals 64. Let us start by looking at the bases of our exponential terms. The first term has a base of 4, which is an even number. The second term has a base of 16, also an even number. The right side of the equation is the constant 64. It is very helpful to express all these numbers with a common base. The smallest integer base we can use for these numbers is 2. Let us rewrite the number 4 as a power of the number 2. We know that 2 multiplied by 2 is exactly equal to 4. Therefore, we can replace the number 4 with 2 squared. Next, we will look at the base of the second exponential term. This base is 16, which we also want as a power of 2. We already know that 2 squared is equal to the number 4. If we multiply 4 by 2, we get the positive number 8. Multiplying 8 by 2 gives us exactly the number 16. This means that 2 to the 4th power equals exactly 16. We can replace 16 with 2 raised to the 4th power. Finally, we must look at the constant on the right side. The number 64 can also be written as a power of 2. We know that 16 multiplied by 2 equals 32. Multiplying 32 by 2 gives us exactly 64. This means that 2 to the 6th power equals 64. We replace 64 with 2 raised to the 6th power. Let us write out our new equation with these base 2 terms. We have 2 squared all raised to the variable power of x. This is multiplied by 2 to the 4th all raised to the x. This entire product is equal to 2 to the 6th power. We must now simplify the terms that have nested exponents. We must be very careful when applying algebraic rules to exponential equations. A small mistake in multiplication can lead to completely wrong final answers. There is a standard rule of algebra for a power to a power. When you raise a power to a power, you multiply the exponents. Let us apply this multiplication rule to our very first term. We have the base of 2 raised directly to the second power. This whole quantity is then raised to the variable power of x. We multiply the exponent by the variable exponent x. This gives us a new combined exponent of exactly 2 times x. The first term simplifies to 2 raised to the power of 2x. We will now apply this exact same rule to our second term. We have the base of 2 raised directly to the 4th power. This quantity is also raised entirely to the power of x. We multiply the exponent 4 by the variable exponent x. This results in a new exponent of exactly 4 times x. The second term simplifies to 2 raised to the power of 4x. Let us write down the simplified version of our full equation. We have 2 to the 2x multiplied by 2 to the 4x. This mathematical product is equal to 2 to the 6th power. At this stage, we can make our equation much easier to read. We will introduce a new variable to substitute into the math. Let us define a new uppercase variable called u for this step. We will set the variable u equal to 2 to the power of x. This substitution will transform our complex exponential terms. Let us look at our first term, which is 2 to the 2x. We can rewrite this term using the power rule in reverse. 2 to the 2x is the same as 2 to the x all squared. Since u is equal to 2 to the x, we can replace that part. The expression 2 to the x all squared simply becomes u squared. Now let us examine the second term in our current equation. This term is 2 raised to the power of exactly 4x. We could also rewrite this using the reversed exponent power rule. 2 to the 4x is the same as 2 to the x all to the 4th. Again, we will replace the 2 to the x portion with our u. The expression becomes the variable u raised to the 4th power. We can now rewrite the entire equation using our new variable u. The left side becomes u squared multiplied by u to the 4th. The right side remains as 2 raised to the 6th power. Let us write the constant on the right side as 64 again. We have u squared times u to the 4th equals 64. We must now combine the u terms on the left side of the equation. We are multiplying two expressions that have the same base of u. The rule for multiplying with the same base is to add exponents. We take the first exponent, which is the exact number 2. We add it to the second exponent, which is the number 4. The sum of 2 and 4 is exactly equal to the number 6. Therefore, the left side simplifies down to u to the 6th power. Our equation is now u to the 6th power equals 64. We want to solve this polynomial equation by finding its roots. The best method is to move all terms to one side of the equals sign. We will subtract 64 from both sides of our equation. On the left, we now have u to the 6th power minus 64. On the right side, 64 minus 64 leaves exactly 0. Our new equation is u to the 6th minus 64 equals 0. We can factor this expression by recognizing a very special pattern. We will treat this as a difference of two perfect squares. Let us rewrite the first term, u to the sixth power, as a square. By exponent rules, u to the sixth is u to the third, all squared. Now let us look at the second term, which is the number 64. We know that 8 multiplied by 8 equals exactly 64. Therefore, 64 can be written as 8 raised to the second. We substitute these squared terms back into our main equation. We have u cubed squared minus 8 squared equals 0. This perfectly matches the standard difference of squares algebra formula. The formula says the first squared minus the second squared can be split. It factors into the first minus the second multiplied by their total sum. In our specific case, the first part is u to the third power. The second part in our formula is simply the integer 8. Applying the formula gives us two distinct polynomial factors. The first factor will be u to the third power minus 8. The second factor will be u to the third power plus 8. We multiply these factors and set the entire product to 0. We are not done factoring because we have another special pattern. Let us look closely at the first factor, u cubed minus 8. The number 8 can be written as 2 to the third power. So this factor is actually u to the third minus 2 to the third. This is a classic difference of cubes, which we can factor further. The difference of cubes formula requires a linear and quadratic part. The linear part is simply the first term minus the second term. In this case, the linear binomial factor is exactly u minus 2. The quadratic part squares the first, adds the product, squares the last. Squaring the first term u gives us u raised to the second power. Multiplying un to gives us a middle term of exactly 2u. Squaring the second term to gives us a final constant of 4. So the quadratic factor is u squared plus 2u plus 4. That completely factors our first original binomial expression. Next, we must factor the second part, which is u cubed plus 8. As before, 8 is equivalent to 2 raised to the third power. This makes the expression u to the third plus 2 to the third. We will apply the standard algebraic sum of cubes formula here. The linear factor is the mathematical sum of the two base components. This gives us a new linear binomial factor of exactly plus 2. We must now evaluate the quadratic portion of this sum of cubes formula. The quadratic part has a subtraction sign for the middle term. We square the first term to get u to the second power again. We subtract the product of the terms, giving a minus to u. We add the square of the second term, which is positive 4. The quadratic factor is u squared minus 2u plus 4. We have now completely factored the entire left side of the equation. Let us clearly write out the fully factored version of our equation. The first factor is the linear binomial u minus the number 2. The second factor is the quadratic u squared plus 2u plus 4. The third factor is the linear binomial u plus the number 2. The fourth factor is the quadratic u squared minus 2u plus 4. The product of all four of these expressions is exactly equal to 0. The zero product property tells us how to proceed from here. If a product is 0, at least one individual factor must equal 0. We must test every single factor by setting it equal to 0 directly. We will start by examining the very first linear algebraic factor. We set the expression u minus 2 exactly equal to the number 0. We can solve for u by adding 2 to both sides of the simple equation. This operation gives us our first potential root, which is u equals 2. Now we move on to the second factor in our long polynomial equation. We set u squared plus 2u plus 4 exactly equal to 0. This is a quadratic equation, so we should calculate its discriminant. The discriminant formula squares the middle coefficient and subtracts a product. We subtract 4 times the leading coefficient times the constant term. In this specific quadratic, the leading coefficient is exactly equal to 1. The middle coefficient is equal to the positive integer 2. The constant term is equal to the positive integer number 4. We plug these exact values into our standard discriminant formula carefully. We must square the middle value, which is 2 squared, giving us 4. We then multiply 4 times 1 times 4 for the second subtracted part. Multiplying 4 by 1 by 4 gives us the integer number 16. We subtract 16 from 4, which results in exactly negative 12. Since the discriminant is negative, there are absolutely no real solutions. We can completely ignore this complex quadratic factor going forward. Next, we will evaluate the third factor from our full factored equation. We set the expression u plus 2 exactly equal to the number 0. We subtract 2 from both sides to quickly isolate the variable u. This calculation gives our second potential root, u equals negative 2. Finally, we must analyze the fourth and final quadratic equation factor. We set u squared minus 2u plus 4 exactly equal to the number 0. We will calculate the discriminant for this specific equation as well. The leading coefficient is 1, and the constant term is once again 4. The middle coefficient is now exactly the negative integer 2. We square negative 2, which gives us a strictly positive 4. We subtract 4 times 1 times 4, which is again exactly 16. 4 minus 16 once again yields the exact value of negative 12. This negative discriminant means there are no real roots here either. We will effectively discard this second quadratic factor completely. After checking all factors, we are left with 2 real values for u. These values are u equals to and also u equals negative 2. We must remember that u is just a substitution variable we created. We defined the variable u as 2 raised to the exact power of x. Let us look at the particular case where u equals negative 2 first. This implies that 2 to the power of x equals a negative 2. However, any real power of the strictly positive number 2 is positive. It is algebraically impossible for 2 to the power of x to be negative. Because of this fundamental rule, we must reject u equals negative 2. This logic leaves us with only one single valid value for our variable u. We will now mathematically use the remaining valid root, u equals 2. We substitute 2 to the power of x back in place of the variable u. This direct replacement gives us the final equation 2 to the x equals 2. The number 2 on the right side has a completely invisible exponent of 1. We can write this cleanly as 2 to the power of x equals 2 to the 1. Since the numerical bases are exactly the same, the exponents must match. Therefore, we definitively conclude that the variable x must equal 1. We have successfully found the one and only real solution to this problem. The final and complete accurate answer to our exponential equation is x equals 1. It is always highly recommended algebraic practice to verify our final answer. Verification is a critical step in any rigorous mathematical problem solving. It ensures that no extraneous roots were introduced during the algebra steps. We will safely plug the value of 1 back into the original given equation. Our original expression was 4 to the x multiplied by 16 to the x. We carefully replace every instance of the variable x with the number 1. The first term instantly becomes the number 4 raised to the first power. Any rational number raised to the power of 1 is just the number itself. So 4 to the first power remains exactly as the number 4. The second term becomes 16 raised to the very first power as well. Using the exact same exponent rule, 16 to the first is simply 16. We now physically need to multiply these two evaluated numbers together. We quickly calculate the final product of 4 multiplied by 16 directly. 4 times 10 gives us 40, and 4 times 6 gives us 24. Adding 40 and 24 gives a grand total of exactly 64. This calculation exactly matches the right side of our original equation. Both sides equal 64, which confirms our mathematics is entirely correct. Thank you very much for watching this complete mathematical derivation today. Please leave a simple like on this video and subscribe to the math channel.